So the steelworks produces about enough energy to heat 500,000 homes every year, which in the middle of an energy crisis and a cost of living crisis is a massive socio-economic benefit. So Task 6 is primarily about thermal efficiency, but it tackles it from two different perspectives. So on the one side, there are some thermodynamic imperatives for steelmaking. It needs to be hot because you need to induce a phase transformation or you need to melt the material. So part of our activity is around tackling the demand and making sure that the heat that we do generate stays in the process. So we've got a demand reduction focused activity, which is really around the insulation materials that are used. They're an often overlooked element of the steel industry, which is strategically very, very important. You've got iron ore, you've got coke, you've got scrap, and then I believe you have refractories, which are those materials that are essentially the interface between the operators and the material that we want to produce. And the interactions between those two things can really define whether or not you have a high quality process that costs you very little money to run, or a low quality process that costs you a fortune to run. Because the amount of heat that is used in these processes, or thermal energy that's used in these processes, is massive. And then the other side of the project is can't contain all of it where you want to. You might like to, but you can't. Sometimes we're deliberately cooling things down, so we're deliberately removing heat, and in other cases you just get heat escaping from the process. So that's how do we harvest that heat and how do we make money from it? So there's two angles to that. One is a novel approach to being able to generate thermoelectric materials and looking at novel formulations of those thermoelectric materials that are earth abundant, non-toxic and low cost, which we need because of the scalability of the steel industry, the size of the steel industry. The other side of that is about thermochemical storage. So the work that's going on in thermochemical storage is really around how we take heat out of the process and store it in a way that allows us to transport it to somewhere else. We're designing these materials that basically allow us to take that heat that we haven't been able to capture or store within the process effectively and then move it around. So imagine it as like a cartridge. You take a cartridge of this material and then you store the heat in it. It's totally cool, so you induce a phase change in the material. You put it into, say, a heat pump, and then you're reducing your electricity consumption on your heat pump and continuing to heat your house. So it's really all the way from demand reduction within the process itself all the way through to trying to generate societal benefits.